This is additional aspects of aqueous equilibria. This is part 1. And basically this section here has to do with buffers, and that's a buffer, in case you didn't know what that was. This follows nicely from the previous chapter because there are solutions that contain what's called a common ion. For a weak acid, it might be something like HA plus its salt, which could be NaA, sodium acid. So this would be a solution of acids or bases, and they contain a common ion. So let's take a look at this. You are given a solution of, let's say, HF, and it has a Ka of 7.2 times 10 to the negative fourth. But in that solution, you've also added its salt, NaA. So NaF in this case. NaF is a strong electrolyte, meaning that it comes apart easily in water. Whereas HF is a weak acid. It does not come apart that well in water, but it does come apart. So we have this NaF at equilibrium Na plus F negative, but it's a strong electrolyte, so most of it goes like that. Then we have HF, which also can come apart, H plus F negative in water as well, but not that much of it comes apart because it's a weak acid. So what are the major species? Na plus, F negative, HF, and H2O. These are the major species. And so what is the common ion? The common ion is fluoride, F negative, and you can see it if you look at both the equations. You will see it's present in one and it's present in the other. So this is called the common ion. This reaction will be driven left towards the reactants due to Le Chatelier's principle. Now, we've already discussed this in the previous chapter at equilibrium. So you're adding something to the product side and it moves the reaction to the left. You've stressed it. This is called the common ion effect. Can you see what will happen? If we add the NaF, it will force the reaction for the HF to go towards HF. So it makes this whole thing less acidic than HF alone because it's driving it to the left. So it becomes less acidic. Interesting. All right, here's George Washington. I don't know why I'm using George Washington, but I am. Okay, so let's work it out to see exactly by the numbers what happens. A solution has 1 molar HF and the hydrogen ion concentration is 2.7 times 10 to the negative 2 molarity. The percent dissociation is 2.7%. That's how much it dissociates. The pH is what is the pH? Oh yeah, 1.57. The pH is 1.57. However, if we add NaF to the solution, 1 molar of NaF, let's see what happens. What will the concentration of hydrogen ion be and the percent dissociation be? And on top of that, what's the pH? So let's take a look at that. Here's your Ka. 7.2 times 10 to the negative fourth is the Ka for HF. And if you don't want to try it yourself, let's just keep going. Major species, you're going to have HF and F negative from the Na plus, and H2O. Please note that the Na plus has no effect, and the H2O is much weaker than the HF. The Kw is much weaker than Ka. So we can discount that as well. So rewriting the equation, this is what happens if we're going by Ka. And Ka, write the expression, is 7.2 times 10 to the negative fourth equals H plus times F negative over HF. Now, oh, there's that foot again. Now I want you to ice it. Do you remember how to ice it? Lay out the equation, spread it out, then initial, change, equilibrium. It's the ice method. I'm going to show you that and explain to you where the numbers come from. So for HF, that comes from the HF, that 1 molar. There is no hydrogen ion to begin with, and at the end, F negative comes from it has a 1.0 from the NaF. Really important for you to take a look at this, to understand this. So now we can put our numbers in to our expression, and those x's are small, so we can discount them, the plus x and the minus x, unless you adore doing quadratics. And the hydrogen ion concentration is as follows. So the pH is 3.14, which is quite different from the other one. The percent dissociation is 0.72%, which is quite different from 2.7. Compared to the original, there is a big effect from adding something with a common ion, a salt with a common ion. We can also use Henderson-Hasselbalch. This is used for calculating the pH of a buffer. Nice handy-dandy little equation. And usually we use pH is equal to pKa plus the log of the concentration of the base over the concentration of the acid. I'll let you figure that out yourself. This is end of part 1. This is additional aspects.